Welcome to Understand the Math. In this Calculus 1 video, we're exploring limits at infinity and horizontal asymptotes. We'll talk about how functions behave as the input value grows very large or very small, look at common indeterminate forms such as infinity divided by infinity and infinity minus infinity, and see how these limits help us identify horizontal asymptotes of graphs. We'll walk through lots of examples so that you can understand exactly what's going on. Be sure to download the free guided notes to follow along step by step. Let's start by looking at limits at infinity and walk through some examples. A limit at infinity describes the behavior of a function as the input x grows larger and larger, positively or negatively without bound. For example, with this function y is equal to 1 over x, we'll look at what happens to the function as x goes to positive infinity or minus infinity. Limits at infinity are really important because they determine horizontal asymptotes of graphs. If we look back up at this graph, this function has a horizontal asymptote y is equal to 0, and we can find that asymptote by looking at the limits at infinity. Limits at infinity are also important for understanding long-term behavior of functions and for evaluating improper integrals. Improper integrals are typically covered in a Calculus 2 course. Limits at infinity can equal a finite number, such as 2, positive infinity, negative infinity, or they might not exist at all, in which case we say that they do not exist and abbreviate it as DNE. The examples that we're going to go over first are limits at infinity that are relatively easy to evaluate. Let's look at our first example. Whenever you evaluate a limit, the first thing that you need to do is substitute in the value that your limit is approaching. In our first example, x is approaching infinity, so that's what we're going to plug in. This is equal to 1 divided by infinity. 1 divided by a really large number is going to equal 0, so our limit is equal to 0. Let's look at our second example. In this example, x is going to be approaching minus infinity, so that's what we're going to plug in. So this is equal to 1 divided by minus infinity. 1 divided by a really small number, such as minus 10,000, is going to go to 0. So that's what our limit is equal to. Now let's look at our third example. In this example, I have x going to infinity, and our function that we're taking the limit of is sine x. Sine x is what we call an oscillatory function, and it's defined to be between -1 and 1. And our function just continues to oscillate between the values of -1 and 1. When we take the limit of this function as x gets really large, that oscillation is going to continue, so our function is not going to settle down to one value. So we say that the limit as x goes to infinity of sine x is equal to DNE, which means that the limit does not exist. When we evaluate a limit at infinity, sometimes it isn't obvious right away what that limit is equal to because it creates what's called an indeterminate form. One indeterminate form that arises from a limit at infinity is when a function f of x is a rational function defined as p of x divided by q of x. And when you plug in that x is going to plus or minus infinity, you get some type of infinity divided by infinity. Another type of indeterminate form is when the function f of x is the difference of two functions, such as p of x minus q of x. For this one, when you plug in infinity or minus infinity, what you're going to get is some form of infinity minus infinity. We're going to look at both of these forms separately, and we're going to start by evaluating limits with the indeterminate form infinity divided by infinity. When you evaluate a limit that has the form infinity divided by infinity, what you're going to do is divide the numerator and denominator by the highest power of x in the denominator. Let's look at some examples so we can see exactly how this works. In these examples, we're asked to find the limit. In our first example, we're taking the limit of 4x minus 3 divided by 2x minus 1 as x goes to infinity. Whenever you evaluate a limit, the first thing that you want to do is substitute in what your value x is going to. So let's go ahead and let's do this. X is going to infinity, so we have 4 times infinity minus 3, all divided by 2 times infinity minus 1. 4 times infinity is going to be a lot bigger than minus 3, so I'm going to write that the top is equal to infinity. And then the same thing happens with the denominator. 2 times infinity is a lot bigger than minus 1, so we can write this as infinity, and we get the indeterminate form infinity divided by infinity. What we're going to do now is divide the numerator and the denominator by the highest power of x in the denominator. This power of x is right there, so we're just going to divide the top and bottom by x. This gives us the limit as x goes to infinity. We're going to take the top part and divide it by x, and then do the same thing for the bottom part. Now we'll go ahead and break it up into pieces. So we have the limit as x goes to infinity. 4x divided by x is just 4, and then we have a minus 3 over x. And in the denominator, we have 2x divided by x, so that's just going to be 2 minus 1 over x. Now we can go ahead and plug in that x is approaching infinity. So this is 4 minus 3 divided by infinity, all divided by 2 minus 1 over infinity. This term is going to go to 0, and this term is going to go to 0. So we're left with 4 divided by 2, which is 2. So 2 is the value of our limit. Let's now look at our second example. This one is a lot harder than the first one. We're going to begin just like we did with the first one, and we're going to substitute in that x is going to plus or minus infinity. This is equal to the square root of 2 plus or minus infinity squared plus 1, all divided by 5 times plus or minus infinity minus 3. Let's look at the numerator first. The biggest term is the first one, 2 times infinity squared. So let's just write this as the square root of infinity squared, all divided by 5 times plus or minus infinity minus 3. The minus 3 won't matter, so we can just write this as plus or minus infinity. So we end up with some form of infinity divided by infinity, which is an indeterminate form. Now what we're going to do is divide the numerator and the denominator by the highest power of x in the denominator, and that's just going to be x. This is equal to the limit as x goes to plus or minus infinity, the square root 2x squared plus 1 divided by x, all divided by 5x minus 3 divided by x. This is actually more complicated than it looks. We need to know how to divide a square root function by x. To figure out how to do this, let's look at the definition of the square root of x squared. You may or may not have seen this before. The square root of x squared is defined to be the absolute value of x, and we know absolute value of x is x when x is greater than or equal to 0, or minus x when x is less than 0. This tells us as x approaches positive infinity, the square root of x squared is going to equal x. And then as x goes to minus infinity, we're going to look at the other piece, and we can write down that the square root of x squared is equal to minus x. Now let's apply this to our limit. Notice that we have a different value as x goes to infinity and as x goes to minus infinity. This means that we're going to have to look at our limits separately. Our first limit is the limit as x goes to infinity, square root 2x squared plus 1, all divided by 5x minus 3. Now we're going to divide the top and bottom by x. So this is the limit. X goes to infinity, square root 2x squared plus 1. Here, we're going to divide by the square root of x squared because x is going to infinity. And then on the bottom, we're just going to divide by x. This gives us the limit as x goes to infinity of the square root. Pulling in x squared, we have 2x squared divided by x squared is just 2. And then we have a plus 1 over x squared. And in the denominator, 5x divided by x gives us 5 minus 3 divided by x. Now, as x goes to infinity, this piece and this piece are going to go to 0. So what we have left as an answer is the square root of 2 divided by 5. Let's go ahead and let's highlight that. Now we're going to look at the limit as we approach minus infinity. This is the square root 2x squared plus 1, all divided by 5x minus 3. Hang with me. I know my students, when I used to teach this in class, felt like this was one of the hardest problems they've done. Since x is going to minus infinity, looking over to the right, we can see from this right here that x is equal to minus square root of x squared. So that's what we're going to divide by. In the numerator, we have 2x squared plus 1, and we're going to divide by minus square root x squared. And then on the bottom, we're just going to divide by x. So we have 5x minus 3 divided by x. I'm going to go down here to the lower left. We're kind of running out of space. Let's rewrite this as the limit. X goes to minus infinity. Do you see this minus sign right there? We're going to take that out in front. So we have minus square root. Now we can take the x squared inside the other square root, and this becomes 2 plus 1 over x squared, just dividing everything. And then in the denominator, we have 5 minus 3 over x. As x goes to minus infinity, this term and this term are going to go to 0, and we're left with an answer of minus square root of 2, all divided by 5. This is an example where the limit as x gets really large is different than the limit as x gets really small. Let's now look at how to evaluate limits that have the indeterminate form infinity minus infinity. To evaluate these types of limits, what we're going to have to do is use algebraic techniques to simplify the limit. Those techniques can be factoring, getting a common denominator, multiplying by a conjugate. I actually have a video on all of those techniques if you need to review that. Let's now look at our examples. In these examples, we are going to find the limit. Let's look at our first one. The first thing we're going to do is plug in that x is going to infinity. So this is infinity squared minus infinity. And this is called the indeterminate form, infinity minus infinity. What we're going to have to do now is look at our function, x squared minus x, and figure out how to simplify that. When I look at that function, I see that there is an x common to both terms. So let's start by factoring out an x. This becomes the limit as x goes to infinity, x times x minus 1. Now let's go ahead and let's plug in that x is going to infinity, and we have infinity times infinity minus 1. So that's just equal to infinity. And that's actually what our limit is equal to. This is an example of a limit that does not exist, but if you can say that the limit is infinity, that is better than just saying it doesn't exist. This just gives us a little bit more information about the behavior of the limit. Let's now look at our second example. Again, we're going to start by plugging in that x is going to infinity. So we have the square root of infinity to the fourth plus 6 times infinity squared minus infinity squared. This is equal to the square root of infinity to the fourth. We're going to ignore the 6 infinity squared because it's a lot smaller compared to the infinity to the fourth. And then we subtract infinity squared. But the square root of infinity to the fourth is like infinity squared. So this is really the indeterminate form infinity minus infinity. Now we have to figure out how to evaluate this. When I look at our function, notice that it has a square root and then it's subtracting something after the square root. That tells us that we should probably multiply by the conjugate. The conjugate of the square root of a minus b is the square root of a plus b. So that's what we're going to multiply by. This is equal to the limit as x goes to infinity, the square root x to the fourth plus 6x squared minus x squared, and we're going to multiply by the conjugate. So we have the square root x to the fourth plus 6x squared plus x squared. We're just changing the sign. Now, this is really important. We can't change the limit. So if we multiply by the conjugate, we also have to divide by that same thing. X to the fourth plus 6x squared plus x squared. Doing it this way, it's like multiplying by 1, and we don't change the problem. Now let's go ahead and let's multiply things out. Just to make it easier, I'm going to use the FOIL method. So we're going to multiply the first terms. That's both of the square roots, and they multiply out to be x to the fourth plus 6x squared. And now we're going to multiply the outer terms. That is the square root x to the fourth plus 6x squared times x squared. Now let's multiply the inner terms. I'm going to go ahead and put parentheses up here to make it easier. The inner term is minus x squared times the square root of x to the fourth plus 6x squared. And then finally our last terms, which is our x squared terms multiplied, which is minus x to the fourth. Now we're going to divide all of this by the square root x to the fourth plus 6x squared plus x squared. Now, the nice thing about multiplying by a conjugate is that things cancel. Let's go ahead and let's see what cancels. Our x to the fourth is going to cancel, and then this term is going to cancel with this term, and we only have one term left on top. Let's go ahead and let's write that down. This is the limit as x goes to infinity, 6x squared, all divided by square root of x to the fourth plus 6x squared plus x squared. Now what we're going to do is we're going to have to plug in infinity again and see what we get. When we plug in infinity, on the top, we're going to get infinity, and on the bottom, we're going to get infinity. So now we have another indeterminate form, infinity divided by infinity. We just talked about this form, so we know exactly what to do. We are going to have to divide by the highest power of x in the denominator, and that's going to be x squared, which is the same thing as the square root of x to the fourth. So we're going to divide the top and the bottom by x squared. So we have the limit as x goes to infinity, 6x squared divided by x squared, all divided by the square root x to the fourth plus 6x squared. That all gets divided by x squared, and then we have an x squared that gets divided by x squared. Let's see what this is. On the top, our x squares are going to cancel, and we're just going to have a 6. In the denominator, we're going to bring in the x squared as an x to the fourth. So this is x to the fourth plus 6x squared, all divided by x to the fourth. And then we have a plus 1. Hang with me, we're almost done. We have one more step to do. On the top, we have a 6. Now we're going to divide out this x to the fourth. This is going to give us a 1 plus 6 over x squared plus 1. Now we can go ahead and plug in. X is going to go to infinity. So this term is going to go to 0, and we have a 6 all divided by the square root of 1 plus 1. So this is 6 divided by 2, which is equal to 3. So our limit is equal to 3. I've graphed this function down here at the bottom so that you can see that as x gets really large or really small, our function is going to go to the value of 3. Notice in the graph that there is also a horizontal asymptote at y is equal to 3. Limits at infinity lead to horizontal asymptotes, and that's exactly what we're going to look at next. We're now going to talk about horizontal asymptotes and walk through some examples. A horizontal asymptote is a horizontal line that a graph approaches as the input x becomes very large, going toward positive infinity, or very small, going toward minus infinity. The line y is equal to L is a horizontal asymptote of the curve y is equal to f of x if the limit of f of x as x goes to infinity is equal to L, and or the limit of f of x as x goes to minus infinity is equal to L. A function can have 0, 1, or 2 horizontal asymptotes. Here's an example of a function that has 1 horizontal asymptote, and that horizontal asymptote is defined to be y is equal to L. In our next picture, I have a function that has 2 horizontal asymptotes. The first asymptote comes from when x gets really, really large, and it's defined as y is equal to some number L1. And then the other asymptote arises when x approaches minus infinity, and it's given by the equation y is equal to L2. One function that behaves just like this and is used in a lot of applications is the inverse tangent function. You may remember studying that back in trigonometry. To actually find the horizontal asymptote of a function, what you have to do is take the limit as x approaches plus or minus infinity. A horizontal asymptote is defined as y is equal to b. In practice, when we're checking to see if a function has a horizontal asymptote, it's common to also check to see if it has a vertical asymptote. A vertical asymptote is defined as x is equal to some number a, and to find a vertical asymptote of a function, what you have to do is set the denominator equal to 0 after factoring out terms that are common to both the numerator and the denominator. I'll show you exactly how this works. Let's look at some examples where we are going to find the horizontal and vertical asymptotes of the curve. Our first curve is defined as y is equal to 4x minus 3 divided by 2x minus 1. Let's first find our horizontal asymptote. Since the power of x is the same in the numerator and the denominator, we can look at the limits as x goes to plus infinity and as x goes to minus infinity at the same time. The limit as x goes to plus or minus infinity of 4x minus 3, all divided by 2x minus 1, is equal to plus or minus infinity divided by plus or minus infinity. So we can just think of this as the indeterminate form, infinity divided by infinity. Since we have the indeterminate form infinity divided by infinity, to evaluate this limit, what we're going to do is to divide the numerator and the denominator by the highest power of x in the denominator, which is just x. We'll write this then as the limit as x goes to plus or minus infinity, 4x minus 3 divided by x, all divided by 2x minus 1 divided by x. This is just the limit as x goes to plus or minus infinity. 4x divided by x is just 4. So we have a 4 minus 3 divided by x. And in the denominator, we have a 2 minus 1 divided by x. 3 divided by x and 1 divided by x are going to go to 0 as x goes to plus or minus infinity. So we just have 4 divided by 2, which gives us a limit value equal to 2. And our asymptote is y is equal to 2. Let's now look at our vertical asymptotes. To find a vertical asymptote, what you have to do is set the denominator equal to 0. Our denominator is 2x minus 1, so we're going to set that equal to 0, and then we'll solve for x, and we get x is 1/2. And that is our vertical asymptote. I've graphed this function so that you can see that the horizontal asymptote is indeed y is equal to 2, and the vertical asymptote is given by x is equal to 1/2. Let's now look at our second example. This example is a bit more complicated than the first one. We're going to begin again by looking at the horizontal asymptote first. Since the numerator and the denominator contain different powers of x for their leading terms, and they're both not even powers, we need to look at the limits as x goes to infinity and x goes to minus infinity separately. Let's begin by looking at the limit as x goes to positive infinity. We're going to divide both the numerator and the denominator by the highest power of x in the denominator, and that's going to be x squared. Let's plug in x to see what we get. On the top, we have infinity cubed minus infinity, and then on the bottom, we have infinity squared minus 6 times infinity plus 5. So what we have on the top is infinity cubed because that's much bigger than infinity. And then on the bottom, we can write this as infinity squared. That's the highest power. So this is going to equal infinity. Now, you can take a more algebraic approach to solving this and divide both the numerator and the denominator by the highest power of x, and you'll get the same answer. Let me just go ahead and do that so you can see. Honestly, sometimes it just depends what your instructor is asking for, which way you have to do it. We're dividing the top and the bottom by x squared, so this is 1 minus 6 over x plus 5 over x squared. This term goes to 0, as does this term and this term. So we're left with the limit as x goes to infinity of x, which is just infinity. And that matches what we got earlier. Now let's look at what happens as x approaches minus infinity. We have x cubed minus x, all divided by x squared minus 6x plus 5. Let's plug in x goes to minus infinity. We'll have to watch our negatives here. We have minus infinity cubed minus infinity, all divided by minus infinity squared minus 6 times minus infinity plus 5. These two terms are our largest terms, so we can ignore all the other ones. And this gives us a minus infinity cubed divided by infinity squared, which gives us minus infinity. So that's our answer. Again, you can get that answer by dividing both the top and the bottom by x squared. Now let's think about what our answer tells us. We found that the limit as x approaches infinity and minus infinity is infinity and minus infinity. That tells us that we actually have no horizontal asymptote. Let's now look at our vertical asymptotes. To find the vertical asymptote, we have to set the denominator equal to 0, but there's a catch. We can only do that after we factor out terms that are common to both the numerator and the denominator. So we're going to have to start by factoring the numerator and the denominator. We have x cubed minus x, all divided by x squared minus 6x plus 5. In the numerator, we can pull out an x, so that leaves us x squared minus 1. And then in the denominator, we can factor this as x minus 1 and x minus 5. Notice that in the numerator, we still have a term that needs to be factored, so let's do that. That's x. X squared minus 1 factors into x plus 1 and x minus 1, and then we'll copy down the denominator, x minus 1, x minus 5, and now we can cross out the terms that are common to both the top and the bottom. What we do next is we take the term in the denominator that's left and we set that equal to 0. And that is x is equal to 5, and that is our vertical asymptote. I graphed this function so that you can see that it has a vertical asymptote at x is equal to 5. And I also wanted you to notice one other thing. Do you see this open circle right here? That is called a removable discontinuity. And it happens when you have a function where you can factor out a term such as x minus 1. This function also has what's called a slant asymptote. That often happens when you're finding a horizontal asymptote and you get that it goes to infinity. We're going to be talking about slant asymptotes later in this course when we talk more about graphing functions. And that's it. You've seen how to evaluate limits at infinity, how to handle indeterminate forms, and how limits at infinity connect to horizontal asymptotes. To really master these concepts, make sure you work through plenty of practice problems on your own. That's really the best way to learn calculus.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.